Okay, so next section, 9.2, the hyperbola. Okay. Get my camera straight. Oh boy. Okay, so we'll begin with another definition. Oh, jeez, this thing is kind of. Sorry. Okay, good enough. Begin with the definition. So the hyperbola is a set of all points such that something holds, some sort of criteria holds. Great, stupid thing. Okay. All right, so definition. Okay. So last time we had the definition of an ellipse was a set of all points such that their distance, such that we had some distance to the foci, the sum of some distance to the foci was equal to a fixed constant. For the hyperbola, it's the difference of the distance to the foci. Okay, so it's a set of all points such that. And again, I'll draw you a picture to motivate the sort of algebraic definition. So we'll still have vertices on this thing and still have foci, but now the foci are going to be on the outside of the vertices. Okay. You can consider like minor vertices, but they're not actually on the graph. Okay, they're more or less just there to help you sort of make a drawing. There's going to be these asymptote figures going through the center. And then the actual graph will be these arms right here and right here. And then on the other side, here and here. Okay, okay, so the definition, the set of all points x comma y, so we can put one point here, this is p, x comma y, such that the distance from P to this focus, so we'll call this F1, minus the distance from P to this other focus, well, this F2, is now equal to a fixed constant. And to make sure it's positive, we'll put it in absolute values. So P F1 minus P F2, absolute value of, is equal to a fixed constant. And again, the fixed constant is 2a, just the same as it was in the case of the ellipse. Okay, so the points, the sort of names of the points are the same as before. For the vertices, you're going to use little a. So this will be little a0. And then this will be negative a0. For the foci, you're using the letter C, so this will be at C0, and this will be at negative C0. And then for the tops and bottoms of this box that helps us draw the graph, you're using the B, the little b letter. Okay, so this will be 0b, and this will be 0, negative b. Okay. Unlike the ellipse, it's now not necessary that A needs to be bigger than B. Okay, that goes out the door. We'll need a formula again, and I don't have a clever way of envisioning this. I just sort of memorized it. It's C squared equals A squared plus B squared. So in order to get the C value, you solve that relation, and you get C is square root of A squared plus B squared. Okay. What else? Well, the formula looks just like the formula from the ellipse, except there's a minus sign in there. Okay? So the formula for this orientation, x squared all over a squared minus y squared all over b squared equals 1. Okay. We can also have orientations where the branches are on the y-axis. And in that case, the y squared term will be positive. So let's just consider that for a second. Okay. So we have the bottom and top where the vertices will be, and some sort of box drawn based off of the B values and the A values. Sorry, it's falling off the page. And now the foci will be on the y-axis. Okay. And the branches as well will be now on the y-axis. So now the points, instead of, A0, it's going to be 0, comma A and 0, comma negative A. And then, of course, 0, comma C and 0, comma negative C for the foci. And then the side points here will be at B, comma 0 and negative B, comma 0. Okay. And then the formula for this will have the y squared term being positive. So before it looked like this, in this orientation, it looks like this. And of course, this will be A squared. Sorry about that. So y squared over A squared minus x squared all over B squared is equal to 1. And it's basically, if you see the y terms positive, you put it in this orientation. If the x term is the positive term, put it in this orientation. Okay. One other tidbit that I'm not going to get too carried away with, but it is required for the homework, the asymptotes. Okay, so I just call this section 2 in my notes. You can kind of get the equation for the asymptotes just by looking at the particular graphs. So in this first orientation, where the branches are on the x-axis, you have kind of this box here, and then the asymptotes going through. We need a formula for the asymptotes. You figure it out using these points. Okay, so this point would be 0b, this point would be negative a comma 0. Okay, and basically you just need the slope. So in general, we have a slope, a point slope form that we have y minus y1 equals m times x minus x1. So I need equations for these asymptotes, these lines that go through the origin here. Okay, so first off, the lines going through the origin will have the point 0, 0. They go through the origin, they go through that point 0, 0. Okay, and then secondly, the slope. So how do I get the slope? Well, you can think about it's, I go up by B and then over by A. So for this first line, I go up by B, and then I go right by A. So the slope is B all over A. And then you just plop this information into this formula, and you get the formula for the first asymptote. y equals b all over a times x. Okay? It'll be, technically y minus 0, which is just y, and then m, which is b over a, times x minus 0, which is just x. And then for the other asymptote, this one going down, you say, okay, it's first you go down b, so the second asymptote, okay, it goes through 0, 0 as well, but the slope is different. This time we go down b and then over a. So down b over a. Negative b and then over a. So the formula will be y equals negative b over a times x. Okay, and now the other orientation. Okay. So we can literally just think about this box at this point. And we're looking for the equations of this asymptote. And of course, the branches of the hyperbola are on the y-axis here. But we're after the equations of these lines, right? So in this orientation, this point here is 0, comma a, and then this point down here is 0, comma negative a, and then these side points are at the coordinates b0 and negative b0. Okay, so again, both of the points go through the origin 0, 0. We just have to figure out their slopes. So the slope of the one going up, so what do? We go up by a and then over by b. So the slope here, a over b. Right? So that tells us the first asymptote is a over bx. Right? And then for the second line, what happens there? This one goes down. So what are we doing? We're going down a, so negative a, and then over by b. So the slope here is down a, sorry, I'm smushing all this in, and then over by b. Okay? So we'll have y equals negative a over bx. Okay, but like I said, on a test, I wouldn't be looking for that information. It may be required in the homework, but me personally, I don't need it. Okay? Now, I want you to show the asymptotes when you go to graph it. Yeah, I need to see that because the branches of the hyperbolas approach the asymptotes as they go further and further out. Okay? So it is required to get an accurate graph of the hyperbola. Okay, so let's move on to look at some of the problems. Where am I? So section 3 now. Graphing, and of course we're going to look at the hyperbolas centered at 0, 0. Later look at the hyperbolas centered at very varying centers like h, comma k. Okay, so centered at 0, 0. The way I want you to do it is sort of locate the vertices, do your rectangle. So first, locate vertices, the major and minor vertices. And then secondly, draw your rectangle. And then thirdly, draw your asymptotes. And then fourthly, draw your branches. Okay. So let's dive in here and take a look. Here's number 13, x squared over 9 minus y squared over 25 equals 1. Okay. So the first thing that's a bit different than working with the ellipses is our a value, and of course we'll want to get our a, b, and c values. Our a value in this case is not 5. It's not from the bigger number. The a value is always from the term that is positive. So here the y term is negative, but the x term is positive. So we'll borrow the 9 for our a. And of course, this term right here is x squared over a squared. So a must equal the square root of 9, which is 3. And then our B value will be the square root of 25, which is 5. And then we need our C value for the foci. C is going to be the square root of A squared plus B squared. So 25 plus 9. And that equals a square root of 34. And approximating that is 5.83. Okay. So our center here, 0, 0, of course. Let's go ahead and start graphing it. So first I want you to locate the vertices, in other words, the tops and the bottom of the box, the rectangle. Okay, so the A value, 2, 3, we have there, and then there. Those are actually our vertices, so I start at 0, and then I move over left and right by 3. And then sort of our minor vertices, if you wish, they are not part of the graph. Okay, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Got one up there and one down there. So I'm going 0 plus or minus 5, comma, whoops. B sub m is 0, comma 0 plus or minus 5. So I'm going up and down by 5. And then finally the foci. So for the foci, I'm going left and right. So 5.83, 1, 2, 3, 4, 5, 6. It's in here. 1, 2, 3, 4, 5, 6. Right here. So what did I do? I went 0 plus or minus square root 34 in either direction. Okay, so now I want to draw my box. And then I want to do my asymptotes. Okay. And then I can do my branches. And the branches get really, really close to the asymptotes, but never touch them. And there it is. Okay, let's do another one, sort of a different orientation now. So this is 23 in the book. We have 9y squared minus 25x squared equals 225. Right? Not in standard form, right? So I want to divide both sides by 225. 9 over 225 is the same as 1 over 25. 25 over 225 is the same as 1 over 9. And we have 1 on this side. So now the y squared is the positive part. So the branches of hyperbola will be on the y-axis. So let's get our information. The a is 5. The b will be 3. The c will be square root of 34. Just a squared plus b squared is 34. An approximation of that is 5.83. And then we can start worrying about our graph. Okay, so for my vertex, the center, of course, is 0, 0. My vertices, now I'm going up and down to get to those points. So I go up 5, 1, 2, 3, 4, 5, and then down 5, 1, 2, 3, 4, 5. So I'm going 0 and then 0 plus or minus 5. For the b values, the minor vertices, I call them, are going left and right. So 0 plus or minus 3, 0. So 1, 2, 3, and then 1, 2, 3. Then for our foci, we're going again up and down. So my foci, 0, 0 plus or minus 5.83. So up 5.83. And then down 5.83. Right there. Get your box. Draw your asymptotes. And then again, your branches will be on the y-axis because the y term is positive. So the branches will approach the asymptotes. Get really, really close, but never touch. And there you have it. Okay, so now we want to look at non-zero, non-origin centered hyperbolas. So section 4. And the resulting formula is very similar to what we did with the ellipse. You're just going to sort of sneak in an H and a K. And let's take a look. So let's pretend our center is right here. And maybe our box is right here. And then our foci right there and there. And then we have our asymptotes there and there. And then our branches, this. Right, so the formula for this guy will be now x minus h squared all over a squared minus y minus k squared all over b squared, and that'll equal 1. Okay. So the center, again, is h comma k. And then to get the vertices, we're moving in the x direction. So we're sort of adding and subtracting on the x coordinate. So by a. And then for the foci, we're just adding and subtracting c. And then for the minor vertices, we're going up and down. So I'm going to manipulate the y coordinate. So k plus or minus b. All right. Let's look at the other orientation. Maybe put it over here. Okay, this time the foci will be on this line parallel to the y-axis. Let's put some minor vertices in there, get our box, do our asymptotes, and get our branches. Okay. So our formula this time, the a will go with the positive, with the y term. Okay, so y minus k squared all over a squared, and then minus x minus h squared all over b squared, and then that'll equal 1. Okay. So for the center, again, it's h comma k. And then to get to the vertices, we're moving up and down. So you're manipulating this y coordinate, this k. So it'll be k plus or minus a. And then for the foci, you're going up and down as well. So it'd be h comma k plus or minus c. And then for the minor vertices, you're going in the x direction. So you're manipulating the h, going plus or minus b. And that's the whole spiel. Okay, so let's look at 2 of these. One where it's kind of a normal version, and then one where we have to complete the square. Okay. Okay, so let's take a look. This is 35. So I have x plus 3 squared all over 25 minus y squared over 16 equals 1. So go after the center is -3 comma, and there's nothing here, so 0. The a value will be from the positive term, so it's 5. The b value is 4. And then c is the square root of 25 plus 16, which is square root of 41, I believe. This is approximately 6.4. Okay, so let's go ahead and start thinking about our graph. Negative 1, 2, 3, 0. Okay, so to get to the vertices, I'm going left and right by 5. So my vertices, I'm going negative 3 and then left and right by 5. So negative 3, 1, 2, 3, 4, 5. And then 1, 2, 3, 4, 5. Okay, for the foci, you're going left and right by, oops, so it's negative 3, left and right by root 41. Let me get myself in the trouble here because I'm smushing everything in. So I go over 1, 2, 3, 4, 5, 6.4. And then 1, 2, 3, 4, 5, 6.4. To get to the minor vertices, then I'm going up and down. So it would be negative 3, comma 0, plus or minus 4. So 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we want to draw our rectangle. And then I want to put my asymptotes in there. Okay. And then finally do your branches. I apologize for smushing this all in. Hopefully you can sort of figure it out. Okay. Okay, so that's sort of your standard example. Let's look at one where you have to complete the square. So there's a little more work. And let's go for it. So 45. We have 16x squared minus y squared plus 64x minus 2y plus 67 is 0. Okay. So we want to group the x terms together, group the y terms together, and then complete the square. Remember, you need a leading coefficient of 1 to complete the square. Here we go. So I'm getting I'm grouping the x terms and getting the constant on the other side. Now I want to factor out 16 and leave some room to complete the square. And here I'll factor out a negative. Leave some room to complete the square. On the other side, negative 64 plus something plus something. Okay, so first, b all over 2 squared is 4 all over 2 squared. 4 over 2 is 2, 2 squared is 4. Okay, so 16 times 4, I'm not just adding in 4, I'm adding in 16 times 4. Okay, so on the other side, I'll get positive 64. Okay, and now I have 2 all over 2 squared, which is 1 squared, which is 1. So I add that in. I'm not adding in 1, I'm actually adding in a negative 1. So on this side, you have to put negative 1. I'm sorry, this should be 67. Sorry about that. Okay. Let's go ahead and factor this thing now. So I have 16 times x plus 2 squared minus y plus 1 squared equals negative 4, it looks like. Okay, we want to get it in the standard form, so I need to divide by this negative 4 on both sides. Okay, and again, I don't want this leading coefficient. I need something in the denominator. I don't want a 16, I want it to be 1. I just want it to be x plus 2 squared in the numerator. Okay, so what I'm going to have to do here is to, what is 16 all over 4? Well, that's equal to 4 over 1. And to rewrite that with the 4 in the denominator, I'm going to have to rewrite 4 as 1 all over 1 all over 4. Okay, so this first term, and I'm going to sort of put the negative in front, it'll be x plus 2 squared all over 1 over 4. And the next term I don't have to change too much, but it is, we do have a negative and a negative here. Okay? So you can think about it, how does this work? Well, it's similar to, for example, if I had negative 1 all over negative 2. Okay? So I can rewrite any fraction by putting the negative in the numerator, out in front, or in the denominator. So I can rewrite 1 over negative 2 as negative 1 over 2. So what is going on? It's really a negative negative. In other words, it's actually just a positive. So the second term here becomes plus y plus 1 all over 4. Okay. And then to get into the hyperbola form, we're just going to use the commutative law of addition. 3 plus 2 is the same as 2 plus 3. To rewrite this guy as y plus 1 squared all over 4 minus x plus 2 squared all over 1/4. Okay, so now I have it in my standard form. I can go out and get my a value is square root of 4, so it's 2. The b value is the square root of 1/4, which is 1/2. And then our c value is the square root of 4 plus 1/4, so 17/4, which is equivalent to square root of 17 over 2. But if you put it into your calculator, it's about 2.06. Okay, so the majority of this graph is going to be in the third quadrant. Let's find the center. So the center is at negative 2, negative 1. So negative 1, 2, negative 1. To get, so what is the orientation? Its branches are going to be on a line parallel to the y-axis. Okay. So to get to the vertices, I'm going to be going up 2 and then down 2. So the vertices, and we're manipulating the y-coordinate. So negative 1 plus or minus 2. So here I go, 1, 2, and then 1, 2. For the foci, you do the same thing, but you use the c value. So the foci will be negative 2, comma, negative 1, plus or minus the square root 17 over 2. In other words, you go up and down by 2.06. So 1, 2.06, and then 1, 2.06. Finally, for the sides of our box, the minor sort of vertices, you're going left and right this time. So it's negative 2 plus or minus 1/2, comma, negative 1. So kind of a really smushed box. Then we, draw your box, get your asymptotes. And do your branches, and you should have it. So the blue part is the only graph. I know there's a lot of stuff on there. The only real part of the graph is the blue. Okay. Great. Well, let's look at one application of hyperbolas. And this story problem seems to come up again and again. So it's sort of a standard issued problem. And I have it in my notes as section 5. I don't know if I'm on track, but okay, so it's an application. One thing about this application, of course, you need to know the conversion from a mile into feet. So 1 mile is 5,280 feet. The deal is, so the problem 61 on page 983. The deal is you have 2 listening stations on the side of a lake or something like that. And so essentially what you have are 2 microphones spaced out on a lake 1 mile apart. And they record an explosion. Okay, so the first microphone and the first listening station hears a sound. So M sub 1 is what I'm counting the first microphone. Here's a sound 2 seconds before the second microphone at the other listening station. Okay. We know that sound travels 1,100 feet per second. We want to determine the possible locations of the explosion relative to the microphones. Okay, so this is a very serious problem. You can imagine the Coast Guard or something like that. They hear maybe a civilian boat is out there fishing and it explodes for some reason, a gas leak, who knows. And you need to optimize travel time for your helicopters. Helicopters only have limited amounts of fuel they can carry. So you don't want the helicopter just randomly out there looking for the explosion. You want to give them a path. And that's what this is going to do. We can actually create a formula for a hyperbola such that we can be sure that the explosion is on the path or the branch of the hyperbola. And then you just tell your helicopter to go out there and follow that branch. Okay, it's probably not optimal, but it's better than just saying, hey, why don't you go out there and look for the explosion? We heard something, I think it's over there. You know, that's not going to help. If they have to sit and hover, they'll go through their gas. You know, they need to kind of have an idea. So that's what's going on here. Let's go ahead and kind of do a schematic diagram to start with. So we have 2 listening posts, and we're going to pretend the listening posts are the foci, all right? And then the foci are hearing this explosion somewhere. Let's pretend it's right here. And they hear the actual explosion at different times. So that kind of tells you that there's we can tell the distance of these lines. In particular, remember, distance equals rate times time. So we could figure out how far away the microphones are from this explosion using this formula, this simple formula you should know from 0965, right? Okay, so let's get at it and see what happens. Right, so microphone 1 hears a sound 2 seconds before microphone 2. The 2 microphones are 1 mile apart, so in particular, this position of the first foci, we can say is 2,640, 0. So this is foci 1. And then the location of this foci is negative 2640, 0. Okay. This tells us that the C value that we need for our formula is 2640. We also need an A value and a B value, and that's where this stuff is going to come into play. So in particular, if you remember from our beginning working with setting up the definition of the hyperbola, the distance, the difference in the distances is equal to 2a. And that's kind of what we're dealing with here. It's saying that M1 hears a sound 2 seconds before M2. So basically, if you subtract the time M1 and M2, it's going to equal 2. And then we could set that equal to 2a and solve for a, right? So let's try that. So in particular, we have the distance must equal 1100 times 2. Okay, so that would be the difference between, so M1 hears a sound 2 seconds before M2. So we're sort of figuring out the distance between, I'm trying to put this in the best phrasing here. It's telling us basically the distance between M1 and M2. Okay? So the rate of sound is the 1100 feet per second, and then the time between the recorded explosion on the in the two stations is 2 seconds. So if you multiply that together, you get 2200, and then that's also equivalent to the difference between the explosion to F2 and the explosion to F1, which we know from our beginning work is equal to 2a. Okay. So well, now we could say that 2200 is equal to 2a, and therefore a must be equal to 1100. Okay, so we have an a and we have a c value. We know from our formulation that a squared plus b squared is equal to c squared. Right? So we can find the b value that we need for our equation. So what do we have then? A squared plus b squared is equal to c squared. So c squared is equal to, or rather we want b squared. B squared is equal to 2640 squared minus the 1100 squared, whatever that turns out to be. I think it's something ridiculous, 5759600. And then we have our formula. So the formula, of course, is just x squared all over a squared, which is 1100 squared, whatever that is, minus y squared all over this thing. And then that'll equal 1. So that becomes our path, which the helicopter can travel on in order to look for any survivors of the explosion out in the lake. Okay. Okay, so that's about it. Hopefully that was somewhat clear.